Kirchhoff's rules for complex circuits. There are two rules. First, the loop rule says that the sum of the electric potential or voltage must equal zero. That means that all of the voltages involved in that loop must all add up to zero. This is equivalent to the conservation of energy law. Now, the junction rule says that the sum of the current moving through any junction must equal to zero. So any current coming in and out of the junction, those currents must add up to zero. And that's equivalent to the conservation of charge. Here I have a complex circuit of 3 resistors. We're just going to call them R1, R2, and R3. And they're being powered by a 12-volt battery. What I've done is I've labeled all the loops using these series of letters. So let's apply the loop rule to each of the loops. There's one loop, A, B, G, H, A, B, G, H. In that loop, we have a 12-volt battery and R1. The 12-volt battery increases the potential, and the R1 decreases the potential. So in that loop, we have 12 minus a drop in potential is going to be equal to 0. The drop in potential, I times R, is going to be equal to V, V1. Now the second loop would be ACFH. So ACFH, we start off with 12. We have R2 and back to the 12. So 12 minus I2R2, I2R2 would be equal to V2. That's equal to 0. And the last loop would be ADEH. That loop, the voltages have to add up to 0. We start off with 12. We go all the way to the resistor, and that'll be a drop in voltage equal to V is equal to IR. So 12 minus the IR for resistor 3 is going to be equal to 0. So those are the 3 loop equations that we can use in order to later calculate the currents moving through each of the resistors. Now the junction rule, what I did for the junction rule is I took this diagram and I redrew it just to make things a little more obvious for you. So as we can see, coming from the 12-volt battery, the current splits. Some of it goes into R1, then it continues, and some of it goes into R2, then some of it continues, and it goes into R3, and then they all come back together and go back into the battery. So what I did is I just kind of repositioned the resistors where we have the current coming out of the battery, they hit junction A, and they split off into each of the resistors, and then they come back together, and then they re-enter the battery. So this is the junction that we're talking about. The junction that sends the current into the 3 parallel resistors. So the junction rule says that all of the current that comes into a junction, in and out of a junction, must add up to 0. So we see junction A, that IT comes into junction A, and I1, I2, and I3 leave junction A. So for junction A, IT comes in, that's why it's positive, minus I1, which is leaving, minus I2, leaving, and minus I3, which is also leaving. These 4 currents must add up to 0. In other words, IT is equal to the sum of these 3 currents. Now, if we look at junction B, we can do the same thing. Junction B, we have 3 currents coming in. The current from R1, the current from R2, and the current of R3. They come together at point B and combine to form the outgoing current. So the outgoing current is negative, and the incoming current, 1, 2, and 3, are all added together, and that adds up to 0. You see that the second statement is redundant. It's really the same statement here. If we multiply this statement by -1, we get the original statement. So all of that makes sense. The current coming into A has to be equal to the current coming into B, and we see that from the diagram because the current coming out of the battery has to be equal to the current coming into the battery.